let's just now have a look at comparing the difference in the reactivity of benzene to a regular alkene. So in our case we're going for cyclohexene, but this is true for any alkene to compare it with benzene. So the exam board might not choose cyclohexene. We've chosen cyclohexene because it looks a bit like benzene. So what happens when an alkene reacts with bromine? Can you draw the mechanism for when an alkene reacts with bromine? And when benzene reacts with bromine, we need to generate the electrophile Br. We do that by taking Br2 and reacting it with AlCl3. If you think that looks a bit weird, you could change it to AlBr3, but you don't need to. Just go like that. Instead, AlCl3Br minus. So we've got these two different ways. So what do our curly arrows do in these two different situations? Well, in this first one, as the Br comes close, it becomes polarised, and then from the pi bond to the Br, and then knock off like that. We're going to have added a Br here and created a carbocation. So the second Br, with its lone pair now, can add as well to the carbocation to give us 1,2 dibromo cyclohexane. We've got an electrophilic addition. So this is an addition here with the benzene. We know that we're going to end up with this kind of structure. And we're swapping the Br for the H. And we're just getting bromobenzene, and we've done electrophilic substitution. So we've got electrophilic addition with an alkene, and electrophilic substitution with a benzene. So why are they different? And it's to do with those pi bonds. Remember that in benzene we've got a delocalized, spread out over all 6 atoms, but in an alkene we've got a localized, fixed on one bond, pi bond. So what could we say? Well, the first thing we can say is that in benzene the pi electrons are delocalized. And in our alkenes, in this case cyclohexene, the pi electrons are localized. So which one has higher electron density? Which one has higher electron density? Electrons per given space. So in benzene we've got 6 electrons over 6 bonds, and in an alkene we've got 2 electrons in 1 pi bond. So in benzene 6 pi electrons in 6 bonds, and in an alkene 2 pi electrons in 1 bond. Which one's a higher electron density? 6 spread out over 6, so 6 divided by 6, or 2 spread out over 1, 2 divided by 1. Which one is a higher electron density? So the electron density is higher in the alkenes, and as a result electrophiles are attracted more and alkenes can polarize Br2. Benzene can't. Benzene needs that catalyst. To react. Benzene can't react with the catalyst. Alkene can react with bromine just at room temperature, but benzene needs that catalyst. Right, Right, we've got one last little extension bit to have a consider. I want you to compare the reaction of benzene with methylbenzene. So I want you to think about what you know about putting methyl groups on things and what that does to the electron density. So wind back your thoughts to when you've talked about alkyl groups and what they do, and tell me about the electron density. So the methyl group has a positive inductive effect. Remember that from alkenes? It has a positive inductive effect. That's going to increase the electron density in the ring. It's pushing electrons into the ring. It's increasing the electron density in the ring. And therefore, electrophiles are more easily attracted to methylbenzene. Or polarized by methylbenzene. So made into electrophiles. So methylbenzene is more reactive than regular benzene. So we find methylbenzene reacts a lot more easily than benzene, and we might not need the catalysts or the conditions.